Okay, so what I want to do in this lecture today is just a little bit review at the beginning, and we move to a new subject, the Laplace transformation. So I will stop the higher order differential equation until the variation of parameters, okay, in which we already have some introductions from our last course. So basically, what we are going to do is we are going to include a function that is we call u, or we look here, we include u, and if we set up some sort of differentiations in terms of y prime, y double prime, and then we see that we can make up some sort of arrangement, and we somehow make this uh, set up an equations and then transform it into a matrix form, okay, to solve this solution. And then we can set up the matrix. We can set up matrix using the Wronskian, and then we can solve this Wronskian matrix with Cramer's rule. Okay. The idea for this Wronskian is we find the Wronskian first. That is, we are going to find the Wronskian, okay, and then we solve the Cramer's rule. Basically, what we are going to do is we change the first column for W1. Okay. We change the first column with the right side. Right side is this one. Okay. We change with 0 and f of x. Okay. Change from this one. Okay. From this y1 prime, change to 0 f of x. And then the second Wronskian, we change the second column. Okay. And this is the second column. Change with 0 f of x. And then the Cramer's rule said that you will get the solution by defining the results from W1 over W for U1 prime. This is actually, if you remember, this is simply uh, like this is the variable that we are going to look for, U1, right? And this is the second variable, right? So this is kind of solving a linear equations, okay? And by doing so, we just using the matrix. Actually, you can use any substitutions, eliminations that you can have. For example, if you want to change for this one, changing that, we know that this is true, right? This is true, and we can substitute. Let's say we substitute the u1 prime, so we will have this, then substitute and solve the equations. That's okay. That's okay. You can do that also. Okay. The point is you are going to solve some sort of system of equation. Okay. Some system of equation. Okay. So this is a system of equation, and we can make them as a linear one, right? So we can just substitute, eliminate, and find the relations between this u1 prime and u2 prime, and then integrate at the end and find u1 and u2. That's still u. We need to find out what is the result. Basically, the result is supposed to be in the results of this. Okay, so u1 will be here, u2 here, and we need to multiply with y1 and y2 from the homogeneous one, from the complementary solutions. Okay, so y1 and y2, let me write here, are from form of fundamental set of solutions that is from the homogeneous one. Okay. Okay, let me give you an example, or maybe let's just review what example we already had last time. So we have this, okay? So basically, you will have choices. Okay? You can choose which method you are going to solve. Okay? If the question is not asking you specific method, you can choose. Like for example, this one, you can choose to start with the undetermined coefficients because it's, I think this part is not too difficult, right? X plus 1 e with power of 2x, not difficult um, to imagine if we use the undetermined coefficient, right? Or directly go to variation of parameters like we are having here. So the first one is solving the complementary solutions from the homogeneous one. So we can set our characteristic equation or auxiliary equation. Okay, m squared minus 4m plus 4 equals 0. And we are having m1 equal m2. The roots are equal. So our solution, we need to multiply with x. Okay, so e with power of 2x, and it is x e with power of 2x. Okay, now we have this y1 and y2. Okay, y1 and y2. And then we can plug in this y1 and y2 to our Wronskian to check our determinant. Okay. And then the determinant is found out to be e with power of 4x. And then we can solve through the Cramer's rule, change the first column and second column, right? And then this will be our result for the determinant for the Wronskian 1 and 2. And then we can divide this 2 Wronskian with the e with power of 4x, divide, and we find this 2 u1 prime and u2 prime. And then we can set up integration for both of this u prime. Okay, so u1 prime integrate, it becomes u1. This is this result. We can have u2. This is the result, and then we can combine all together into our sort of equations here. Okay, and we can have our general solution, okay, which is combined with the complementary and the particular solution. So we have to combine both of them to make the general solutions. Okay. Let me give you a little examples, okay, to give you more familiarity on what this method is. Okay, let me check. Okay, let me just go. Maybe the more obvious one. Whenever you see any differential equations, that is, for example, you have y double prime um, plus y equal to, let me check, we have the secant x tangent x. Let's say we have this uh, differential equation. Okay. Now, if you are going to use the undetermined coefficient, you will get some difficulty because of this, of the secant and tangent. So one way to solve is, I think the easiest way is to the variation of parameters. Okay. So first, checking. So let me write here. Step 1, solve the homogeneous form. So we have the auxiliary equation. So m squared plus 1 equals 0. So we know that this m will be plus minus imaginary number, right? Remember that when you have this imaginary number, if it is just only the imaginary part, which means this beta, this only beta, then alpha is 0, then beta is 1, right? So we can just directly write the complementary solution c1 cosine x plus c2 sine x. You can write not in order, like sine first and then cosine at the second one, that's fine. Okay. But you need to be consistent in all your calculations. Okay. The final results should look similar or looks the same. Should looks the same. Okay. So from here we get the sort of idea that y1 probably cos x and y2 is sine x. And then we can move to just taking the Wronskian, taking cos x and sine x. And in the second row, we will have the derivatives, so negative sine x and then cos x. And then find the determinant, so cos squared x minus minus, so plus sine squared x. So it's just 1. Okay. So it's just 1. So we just need to calculate the W1, W2 because the Wronskian is just 1. So W1 we can set up, let me write here. We can set up this becomes 0 and the f of x is secant x tangent x, right? So we are only having the negative sine x multiplied with secant x tangent x. Or we can have secant is 1 over cos, so it will be minus tangent squared. Or this will be tangent squared plus 1 is secant squared, right? So secant squared minus 1. So this will be 1 minus secant squared. Okay. This is, let me just write u1 prime. Okay? Because it's basically divided by 1. It's divided by 1. This is equal 1. This is, okay. And W2 okay, we can set up directly u2 prime is cos x secant x tangent x, right? And with this is canceling cos and secant, so it's just tangent. Okay, we got this 2, then we integrate. Okay, we integrate. So u1 is integrations of 1 minus secant squared x dx. So u2, let me just solve this first. This is x. Secant squared is tangent, right? Integration. And u2 is integration of tangent x dx. How to integrate tangent? If you remember, we can set sine x over cos x dx. And we can set up the substitutions, right? Substitutions. So let's say substitute by the cosine. So du is negative sine x dx. So we will have u2 is negative. Negative 1 over u, yeah, so we have negative ln. U is cosine x. Okay, that's the result. So u2 is negative ln cosine x. Okay. So we can set up our final solutions. That is combining the complementary and the particular solutions. So the complementary will be c1 cos x plus c2 sine x plus. Remember that we need to write, maybe I can write the particular solution here. u1 need to we multiply with y1, so x minus tangent x cosine x plus sine x, or maybe negative. So we can write down that this is x cos x minus sine x minus sine x ln cos x. Okay, that's the general solution. So it is important to note that because you already know the homogeneous one for this, okay. So whenever you have the three case, remember the three case. If you have so first case, distinct root, right? The second case is the equal roots. Third case is conjugate complex. Okay. Number one is going to be okay. You're just having the solutions will be, for example, c1e with power of something plus c2 with power of something. That's solutions, right? When you have the equal roots, remember the rules of duplicity. When you have duplications, you need to multiply with x, or if you still have some duplication, you need to multiply again with x. So x squared, x cubed, x4, and so forth and so on. And for the conjugate complex, remember that you can solve it through Euler formulations. So whenever you have the alpha, this case is alpha is 0. Whenever you have alpha, then the alpha will be in terms of e alpha x, right? In front of the beta is here is cos and sine here. Okay. Okay. Okay, I think maybe do you have any specific questions regarding this chapter, higher order differential equation? Do you have any comments or anything that you still has some questions? So basically, as long as you are following the procedures, then you will just and you note some specific rules, then I think it should be okay, should be fine. And the rest is just basic calculus like derivative integrations. You need to be aware of that. Okay. Okay, if there's no questions, we can move to Laplace transformations. And maybe this course today, we are just looking at the introduction and some sort of the definitions. Okay, the definitions. What's the meaning by Laplace? Why we need that Laplace transformation? Okay. Okay.
Professor, I have
Yes.
a bit question.
Mhm.
Can you explain the use of word skin a bit? Like, what is the use of word skin a bit? Like, just a bit.
You mean which part?
Like the word skin. Like, what can we use with it?
Oh, I think uh, for some, because these two methods, the undetermined coefficient and the variation of parameters, sometimes some equation we can use both. You can just choose. But what I want you to take care is this particular solutions, okay? The forms, okay? Not necessarily memorize all of this, but just looking at the forms. Okay? So for the some sort of we call this is for undetermined coefficient. So if we want to find a particular solution, we can just look on the structure. Okay, the structure. G of x is the right side of the equation. So this is usually differential equation. For example, like this. It has its function on the right side. So first thing, rearrange your equations. Make sure that you can um, make it out the g of x to the right side. Okay, and then you can look the structure. Okay, now the g of x can be many forms. Okay, can be many forms. For example, if you have a constant, a linear equations, or polynomial in general, we can just take it based on what the polynomial's degree. Okay? This is depends on degree of polynomials. All right. If we have trigonometric like sine or cosine, we can make it into a cosine 4. This is using the for x, and b sine. Okay. Both need to be the same. Okay. So sine and cosine, they have both. They need to have sine and cosine at the equation, right, for the particular solution. And then when you have exponent, then you will have a constant multiplied by exponent, because remember, exponent when you derive is their it will bring their own original equations, right? Okay, so you need to include the e with power of 5x. Now if we combine, okay, we have linear equations and then multiply all with the exponent, the same exponent. What we can do, we can make it just linear and exponent. Okay? The same thing when you have a polynomial, you can have a polynomial and an exponent. Now, what will happen if we have the e with the trigonometric? We have e and trigonometric. Then we can just multiply with e, the equations. I think that's quite easy to look at, right? And then we have polynomial and trigonometric. Then we can just multiply both cosine and sine with some polynomial equations, okay, based on their degree. So here is degree of 2, same, okay, depends on the questions. And the next one, we have x, we have e. So we have linear equations, we have e, we have cosine. Then we can just multiply linear, exponent, and cosine, and the sine, the same form, okay, with different constant. The same structure. Okay, so for most of this, okay, linear, polynomial, constant, exponent, sine, and cosine, you can transform directly, or you can predict the undetermined coefficient with some sort of structure. Okay, so like this structure here, all the structure that can have our particular solution. Okay, and then you can just solve it using undetermined coefficient, equaling left and right, make it the same groupings, find A, B, C, D, right? Find the constant. That's what you do. Okay, the difference is if we are having some sort of functions, for example, the g of x, the example that I gave you, if this is tangent x, or maybe secant squared x, or maybe secant x tangent x, or maybe some sort of combinations that when you think on the structure using the undetermined coefficient, probably you will have some difficult times. Okay, so when that happens, go to the variation of parameters. Okay, go to the Wronskian. Okay? Go to Cramer's rule, solve the Wronskian, solve the u1 and u2, and make it the variation of parameters. So let me write here. If you have this, then use variation of parameters. Now, the use of variation of parameters is basically we are going to find we are going to assume that our yp, let me write here, our yp is y1 u1 plus y2 u2. Okay, and the idea is we need to find u1 and u2 through some sort of this Wronskian and determinants, okay? And using Cramer's rule. When we find the u1 prime and u2 prime, we integrate both and we get u1 and u2, and that is our particular solution. Okay, okay, I think that's the general concept, okay, for how to use this forms. Okay? So my suggestions, the idea is first, you can just check through the undetermined coefficient. Okay, checking through that, and if it's okay, then move to variation of parameters. Okay, if it is homogeneous equation, I think you can just go directly solve through the constant coefficient. I think that is our complementary here. Okay, if we have the homogeneous one, I think it's already described previously. Right? Okay, I think that is the differences, okay, for undetermined coefficients and variation of parameters. Of course, if you would choose all equation with variation of parameters, you can do that. You can solve all equation by variation of parameters. Okay? But again, sometimes when you do the matrix, maybe it can take times and maybe a little bit tough sometimes. So you choose just undetermined coefficients to make it easy. Or if you think that undetermined coefficient may be a little bit difficult in some cases, then go to variation of parameters. Okay. Okay.
Okay, Prof, I got it. Thank
Okay.
you.
Okay. Okay. The table, I think, it's important here. So later today, I will upload the second notes. So the first note I already upload inside your quiz, not quiz, the homework folder, the notes. This second note I will upload later on, while giving you another homework. So aside from the quiz that ends this Sunday, I will give you another homework. We'll give you a couple more days for next week. So it's just to help you to solve some higher order differential equations. Okay. Okay. I think we can move to Laplace. Okay, Laplace transformation. So the idea, okay, let me give you just the summary, okay, for the idea why Laplace is important. Okay, so notice that um, we have differential equations, right? Basically, we have differential equations. So we have problem, we have differential equation that need to be solved. And differential equation means that probably we have like y double prime plus 4y plus 2 equals something, right? So the idea behind the Laplace, okay, I think for second order, I think it's still simple. But when you have higher order, like 5, like this, it becomes more and more ambiguous, and it's not easy to read the structure. Right? So the idea of Laplace is transforming differential equations into algebraic equations. That's the idea. So we transform into algebraic equations, we compute a little while, and we transform back to its original structure using the inverse of Laplace. And that's how we are going to do in most sessions in the Laplace transform. Okay, let me just give you an introduction that basically the transform, or let me write, so transformations. Okay, let me write transformations. Basically what you did in calculus, like you have x squared, and then you make the using some operators for derivatives, and it's become 2x, right? Or if you have x squared, you integrate, and this become the new functions, right? You can say it's a new. So the derivative integration itself is also a transformation tool, right? You can derive, you can integrate, and in some sort of way it's transformed some function into another functions, right? Okay. And let me give you just the basic definitions that we are going to use uh, as a Laplace. Okay. Okay. If function of t defined for t less greater equal 0, improper integral from 0 to infinity, let's say some k function of two variables as t, function of t dt. Okay, let's say we have function k defined as, okay, let me write again this k as t f t dt equal limit, let me use p. Usually we are using t for improper, but let me just use p because t is already inside as another function. So this is 0 to b, and k s t f t dt. Okay. Now what is k? K is defined as maybe let me go right a little down here, and let me just give definition on k. So a definite integral, let's say we have from a to b of k, st ft dt. We say that if we have this integral, the definite integral, this will transform, okay, this will transform function of t into a function of variable s. Okay, as example, let me go. Sorry. Let me move this a little bit here, and let me give you. Okay, if we have the thing, let me give you what is the idea or why we are doing all of this. Okay. Okay, sorry. All right. Check. Okay, if the function of xy, this is function of two variables. Then partial, let's say some kind of a partial definite integral of f with respect to one variable. This will lead to function of other variable. And I hope you understand what this means. Okay, let me give you the idea. If we are having integrations 1 to 2, let's say we have 2xy squared dx. What will happen? We can hold y as a constant, like when you do the partial derivatives, or if you remember what we are doing in the previous chapter, okay, the exact equations, right? We're doing some sort of partial integrations, right? Well, there's no such thing as partial integration. That's just a concept, like this one. Then this will be, those y squared is still there, and x squared, this is actually x squared, but we compute 2 and 1, so this will be 3y squared. Okay, so if you look at, this is function of two variables, right? And then this is the integrations that we are going to integrate, the variable that we are going to integrate. We will transform, okay, we will transform these functions into y. Okay, now let's look here. This is the same thing we are doing. This is the function that we are going to transform. We transform from t to s. Okay, so here we transform from x to y. Okay, here we are going to transform from t to s, and that's the Laplace. So the basic foundation of Laplace. Okay. Now this is just taking any number, right? Any a, any b, any constant. But when we are dealing with the Laplace, we are always dealing with the interval from 0 to infinity. Okay, that is defined in here. So we are particularly interested in the interval from 0 to infinity. Okay. We say in the improper integral, when you deal with improper integral in your calculus, we say that limit exists, then the integral is convergent. And if limit doesn't exist, then it's divergent, right? Well, this limit in our discussion for today, it will be exist in general for certain values of the variable x. Okay? And now we need to decide the Laplace transform is just specific at a particular function for k. Okay. Okay. I think if you want to take notes, I think the basic definition is important if you want to understand the Laplace. But the Laplace itself is not this. This is just the general forms. Okay. Okay. Now the Laplace itself, we choose the function k as e with power of negative st. This will give you special transformations, okay, for the integrations. Okay. Then let me give you the definition for Laplace. So let function f, let f be a function defined for t greater or equal to 0, which means from 0 to infinity. Okay. Then the integral now Laplace, we write the Laplace with some sort of letter L with the curve like that. And we say that this is the Laplace operator or Laplace transform. And then we write inside the bracket is the function that we want to transform. Let's say our function is f of t. Like that. Okay, the definitions is based by the improper integral. This is integration from 0 to infinity of e negative st ft dt. Okay, and this integral is said to be Laplace transform. Transform of f, provided integral is convergent. Yeah, that's the definition. Okay, now for some sort of period of time, we are going to deal with some sort of functions that usually appear and we can transform immediately. So we are going to solve some for some functions, and we are going to write necessary functions that in the future we are going to use like some sort of table, like a table of transformations. So usually we write the Laplace with this L like that, and then let's say if we write the ft, the result is, let's say the result is another function, the capital F, but change its variables. Change with F. Usually, to make it easy to look at the structure, or the capital, like this is the small f, this is becoming capital F. Usually that is the case that we are going to write, okay, to help. So transform the small function to be capital and then having different variables from t to s. Okay. Okay. Let's go for some example using this Laplace transform definitions. Okay. So for example, if you want to Laplace transform a constant 1, the function is just a constant. Okay. Then we can take this 0, infinity, e, negative st. Let me just write 1 as here to make sure you understand. And then take limit. But actually, this limit writing you can sort of you can skip, but keep in mind that when you're integrating and when you're doing the improper integral, there is a limit there, just to make sure that the equation is easy to compute. Okay? So you can actually you can skip your calculation with limit, okay? And just write at the end and put in the limit. I think that's still okay. Okay, let me just write here 0b and e negative st dt. Okay, let's just take integration with respect to t. Okay, so we are going to have s as our constant, right? So this will turn out to be it's negative e negative st, and then we have over s, right, as our constant. Differentiate st becomes just s and put down for the integration, and then take from 0 to b, and take one by one. Let me go back here. So input b, this will be negative e negative sb, right? This is over s, and then minus, put 0 minus 1, so plus 1, right? Now look at this and this, right? So this negative e negative sb we can write as negative e sb, right? So when the b is going to infinity, this whole thing is going to be infinity, and this is going to be 0. Okay, that's the definitions in the improper integral, okay, if you remember. So we can set up this as a 0, okay, by a limit, and the result is just 1 over s. So when you have a constant, you can so for example, if you have 4, you can over s, okay. Okay, this is, we are using a limit, right? But in the next sessions, I will just skip the limit writing, but you need to keep in mind that there's a limit there, okay? Just to make it short because all these computation and calculations. Okay. So we are going just to write integral 0 to infinity as it is. Okay. But just to remember that there is a limit there, then we need to make sure that it's converted. Okay. Okay, let me move next. Okay, we move on. Okay, let me try a plus. Okay, maybe keeping a concept. If you have e with power of, let's say, lambda t, lambda is a constant. Lambda is arbitrary constant. Okay, now this means we are integrating from 0 to infinity e negative st, and then the function, we'll write the function here. Okay. E with power of lambda t dt. Okay. Okay, we can combine these two exponents, right? So e, we can combine and make it, it's actually negative st plus lambda t, but let me just factor out the t. This is negative s negative lambda, right? And then dt. Okay. Okay, now to solve this, remember this is just a constant, so we have to integrate with respect to t, and s is actually a variable, but we treat as a constant because this is we partially integrate some sort of. So we can use substitutions. Substitute all of this, and du will be, we treat s and lambda as a constant. So dt is negative, right, du. So we can write this is e u, and this will be negative du. E with power of u is just e with power of u, so we are going to write as it is, e, and then I think we can get the integration directly, so we can write s minus lambda, and then this is e negative s negative lambda t from 0 to infinity, right? negative s minus lambda. Okay, we plug in infinity because it has negative and it's have 1 over e infinity, it's becoming 0, right? So it will be a 0, right? So 0 and then minus 1. So this will be 1 over s minus lambda. And this becomes an important component. Okay? So whenever you have e with power of a constant multiplied with t, and you want to transform using the Laplace transform, this you can directly get this. Okay? So what basically saying from here, you don't really need to calculate all with limit unless you need to prove. But you can directly just say that the Laplace transform of e with power of a constant t is just 1 over s minus a constant. And this will be valid for s that is greater than lambda. Okay. So if you have Laplace e with power of 60, for example, then this will be 1 over s minus 6. And if you have e with power of negative 2t, this will be 1 over s plus 2. Okay. Now we get the second transformation in Laplace. So first is transforming a constant. Second is transforming the e, the exponent, okay, exponent with power of functions t. Okay. Let me wait for a while if you want to take notes here. So that's the idea of Laplace. Okay, we transform from function of t to function of s. Okay. Maybe before we continue, is there any question or maybe if you have something missing from this Laplace? This is just introduction. The practical way to use this Laplace is basically just using the Laplace symbol, your function, some sort of functions, and transforming it to another functions in another variable. Usually it's transformed from t to s, okay? But actually it can be any variable. But for just introduction, I would just use t to s for all aspect, for all example. Okay, we will move to another general formula for the function, okay? And then we are going to develop what the Laplace transform, okay, of that formulation. Okay, we start with transforming function of t with power of n. Okay, n is a power, so n is positive. Okay, we define as positive. So we can say that if we want to put into our Laplace integrations, put e negative st and t with power of n dt. Okay, how to solve this. N is a constant that is positive. S is also in integration. We can treat S as a constant. We can just focus on T. Okay. So how do we solve it? Any idea? Any idea how to solve this? So we have E, we have T with power N. Because I think in your textbook it didn't really show how you are able transform the general forms. It's just giving you the example. Like for example, your textbook just showing you the if you have just t, okay, Laplace t, or Laplace t squared, okay, using some basic integration. But I will just show you. Let's just use the general form t with power of n. Okay, so it can be t, it can be t squared, it can be t cubed, it can be t fourth. Okay. Now we can solve this through integration by parts. Okay, so let me write here. We can integrate by parts. Integration by parts. As I mentioned, I think in the early classes that we are going to, well, I want you to use, okay, in integration by parts, we can set up some sort of which element that we need to derive and which element that we need to integrate. I think for exponent, it can be put into differentiate or integral. No, it doesn't matter. It doesn't matter for exponent because the exponent will give another exponent as a result, right? But for t with power of n, for example, if you have t, if you derive it will be 1, if you derive it will be 0, right? So it's better to take this kind of functions into derivative. Okay, so let's take this t with power of n here. And integration is e with power of negative st. Take derivative, so we have positive, negative. So take derivative, so n going down, okay, or maybe let me write n, and then t, and then n minus 1, right? That's how I just write. The e, this e, we write e, and then we need to have negative and divide by the differentiate here is s, right? Okay, I think we can set up this elements and setting into our equations, right? So this will be Tn and so t with power of n divided by s e and negative st evaluated from 0 to infinity. Of course, you need to remember the infinity here means that there is a limit there. Okay, I will just skip writing the limit, okay, to make it short. Okay. And then minus the plus, okay, integrations. Still, we are going to write this n t n minus 1 divided by s and e with power of negative st dt. Okay, this seems we are having another integration. Okay. But let's check the left side here, the left equation. We put infinity. If we put infinity, what will happen? So if we put the infinity to the e, okay, Because if you remember, okay, you have a power function, you have a power, you have an exponent. Remember in calculus, when you have this kind of limit, when you have this kind of limit, the one that is going change faster is the exponent, right? If you remember. So we deal with the exponent first. Okay? This exponent we can write 1 over e as t, and the same thing will happen with the previous case. It will be getting to be 0, right? When you plug in infinity, it's getting 0. So this whole statement on the left will be getting 0 because of the exponent. It push the graphs going to be 0, okay, all at once. So this whole thing is 0. Okay. Now, we still have the other equation here. Okay. Let me just take the n and s outside because that is a constant. So n over s. So this is what we have left. Oh, sorry. Okay, now we have this. So in some way, we are having, when we have t with power of n, we stuck in this results, right? And then what's happening? You could try to integrate by parts this whole integrations, but you will find exactly, okay, if you find here it's exactly, so I believe you would find that if you have t or maybe let me just give you this conclusion, okay, that this is, okay, this part, this integrations is Laplace of t n minus 1. Okay, so the Laplace of t with power n is equal n over s Laplace of t with power n minus 1. If you do the t n minus 1, if you do the integration by parts, you will get n over s and then n minus 1 t n minus 2. And you will notice that it will going recursively. It will going recursively. And when you have, for example, another one, let me just give you the last one here, n minus 2 for this one here, then you need to multiply with n minus 2 in the front. Okay. So what is technically happen? Okay. When you have n, or let me use the other one here. If you have n, okay, you will give n here, okay, n over s. S is doesn't really matter, so n will be here. Okay. When you have n minus 1, you will give this n minus 1 through this n minus 1 here, and n is still there and s still there. When you have n minus 2, you will give this n minus 2 exactly here, and this will give you another Laplace of t n minus 3. Okay, So if you do all of those things, we can simply conclude that when you have Laplace of t with power of n, this will give you an n factorial. Oh, sorry. S is multiplied with another s from this s minus 1. So s squared and s cubed. Sorry, I didn't mention before. So here the conclusions will have s with power of n, and then Laplace of 1. Or we can simply say the n factorial divided by, because Laplace 1 is 1 over s, then multiply with s with power of n, this will be s n plus 1. This is true for s is greater than 0. Okay. Okay, any questions? I hope you get the idea. Okay, you have to get the idea of what I'm doing here. So let me just give you a recap for what we are doing here. So we have the Laplace transformation for t with power of n. N is a constant. It can be from constant that is greater than 0, which means it's positive. So if we transform that Laplace, this t with Laplace, we take integration by parts. Okay? We take some time to integrate, and then we are having the results of n over s, and then you still have the integration from 0 to infinity t n minus 1 e with power of negative st, which means that this is actually a Laplace of t n minus 1, right? You see the structure. Okay. Now, in some way that you can write down this relations between the Laplace t with power of n with t with power of n minus 1. If you try to solve the t n minus 1, you will get the same idea, because if you think the t n minus 1, if you try to derive, this will be n minus 1 and then t and then n minus 2. Okay, so that is why we need to multiply with n minus 1 here. But since it has another e with power of negative st, and you will get s from the integration, you will see that s is going down, right? So you need to multiply s one more time with and become s squared. Okay, that's why we have the s squared, s cubed. Okay. Or if you would like to try, you can integrate by parts for n minus 1, n minus 2, and n minus 3 if you want. Okay? You will get the exact same conclusions that stated that the more you have, like n minus 1, n minus 2, n minus 3, you will have some sort of this n, and then n minus 1, and then n minus 2, and then n minus 3, and then you can have as many as you want, right? And this is simply the n factorial, the n factorials. So we can stop the recursive. We can stop this with just giving the n with factorial and over s with power of n. And of course, we need to multiply with the Laplace one, okay? Because it still has the Laplace on this side, and we know the Laplace of constant is just 1 over s. So we can just stop and make this conclusion. Okay. So as an example, if you want to Laplace transform t squared, this will be 2 factorial divided by s with cube, or we can just solve this to s cube, or if we have t with power of 4, this will be 4 factorial, and s with power of 5, this will be 4 by 3, 12 by 2 is 24, over s with power of 5. Okay. Okay, there will be another element. Okay. Okay, any questions? Okay, if not, then I will continue. So we have the constant, we have the exponent, we have the e with power function, and then what we are going to do next is the geometry, the sine and cosine. Okay. Let me give you just a cosine. Let's say we have a beta t. Okay, let's say we have a beta t. So beta is, let's say, just a constant, arbitrary constant. Okay, let's start with the integral e negative st and cosine beta t dt. Okay. Okay, same thing. Integration by parts. Okay, now we have cosine, we have e. Both of this is we can differentiate and integrate many times, right? But let me just write the cosine in these integrations, and differentiation is just e. This will be resulting in negative s e negative st. This will result in sine beta t over beta. Okay, this is positive, negative. We multiply, cross multiply. Then we can write e negative st sine beta t over p and then from 0 to infinity. Okay, maybe we can solve this, or maybe let me write this is plus s over b e negative st and then sine beta t dt. Okay. Okay, let me just look at this, and then let me just take infinity inside and just to give you the form that this is negative infinity sine infinity infinity, okay, 5 by beta minus e with power of 0 sine 0 divided beta. This part, as I mentioned, the exponent and this trigonometric, this exponent reduced into 0, okay, because of that exponent property. And this part, sine 0 is 0, so the whole thing becomes 0. Okay, so this is going to be 0. And we are going to focus on here, in which we have s over b as a constant, and we have 0 infinity, and we have e negative st sine pt dt. Okay? Okay, now we have this another integrations. That is, if we look at the functions and the elements inside, that this is at Laplace of sine, right? Okay, it's a Laplace of sine. So let me write this Laplace of sine, and let's try to, again, integration by part. Okay, so let's try to integration by parts, and then same way we take the e integrate become negative cos beta t over b, and this will be negative negative s e negative s t, like that, and then make up the so this is the just or maybe let me write here Laplace of sine beta t. Okay, so we are going to have, as usual, the negative 1 over b e negative st and then cosine beta t from 0 to infinity. And then now it's plus minus, right? Minus s over b cosine beta t e negative st dt. Right. Now solving this one here, plugging into infinity, it will be resulting in 0. So but let me just write down here. Zero, 0. Okay. So this will be 1 over b. This will be 1 over b. And this part here, we can say that we can factor out s over beta, and it gives the e negative st cos beta dt. Okay, we got another Laplace cosine beta over here. Okay, so we can use this this 1, so this 1 over beta minus s over beta, Laplace of cosine beta t. This is our Laplace of sine beta t. Okay, we can use all of this and then substitute into our Laplace of cosine beta t. Okay, let me write here Laplace Laplace of cosine beta t is equal s over beta, and multiply with 1 over beta from this side here, minus s over beta. Or let me write completely to help you remember that this is from s over beta. This is Laplace of sine beta t. Okay. So we can write here, this is Laplace, of cosine beta t. Okay. Okay, so we try to multiply. This will be s over beta squared minus s squared beta squared Laplace cosine beta t. Okay, and this is still Laplace cosine beta t, and we can simplify it. We can move out the s squared over b squared going to the left side, and later we are going to factor out. So Laplace of cosine beta t is minus 1, right? This will be s squared minus beta squared over beta squared. Okay. And then we can take this and write the Laplace of cosine beta t is equal s over beta squared divided by s squared minus beta squared over beta squared. So this will be cancelled. So we can have our Laplace as s over sorry. It's plus, sorry. It's plus, right? Let me check. Yeah, it's plus. Why I'm writing minus? Okay. So it should be plus. So s squared plus beta squared. Similarly, the sine beta t is going to be, or we can just write the L cosine beta t is s over b of Laplace sine. Okay? So Laplace of sine, we can just multiply with beta over s. So this will be beta divided by s squared plus beta squared. Okay, maybe I will write the conclusions in the next page. But let me just stop this page here. Okay. Oh, I just read your question, then. The third case. What do you mean the third case? This example, the third case. Which one? Oh, okay. The the Ron. You mean the Wronskian? The Wronskian? Oh, you already got it. Okay, okay, okay. Okay. Now let me make conclusions and write down what it means. Oh, maybe wait for a while. I need to charge my pencils. Okay, let me charge for a while. Okay, so basically, for some functions, a constant, linear, power functions, exponent, sine and cosine, that are they are all the basic for Laplace. If you can remember, using just by looking at the functions, then I think that's okay. But if you still want to use some table, you can write in a table. Okay, write in a table. I think in the Laplace, um, for Laplace, inverse, and then additional property, I think still okay. But I think for the Dirac delta, if we not really have much time for Dirac delta, I think we can skip and move to the next section. So we are just having the definition, the inverse, some theorem for translations, and some additional operators. Yeah, Dirac delta, I think I will just skip that one. But we are just see if next week we can make it, uh, we smoothly make it into the inverse and the translation and the additional operators. I think uh, we can have the Dirac delta. But if not, we can skip. Okay. Let me check my Apple pencils. Let's go 19%. Okay, let me just write a conclusions. So this is Laplace of cosine. This is Laplace of sine. Let me write a conclusions that is, we call the table of essential transformations. For Laplace. For Laplace. So we have the Laplace of a constant, right? C is arbitrary constant. We have C over S, right? Or maybe let me write. Yeah, maybe here. And then Laplace of E with power of lambda t, where lambda is also arbitrary constant. This will be equal to 1 over S minus lambda. And when you have Laplace with t power of n, you will have n factorial s n plus 1, where n should be positive. And when you have the Laplace of cosine, let's say beta t, this will be s over s squared plus beta squared. Beta is a constant. And when you have sine, you will have beta over okay, just some example. You have Laplace of 3. This will be 3 over s. Okay. You have Laplace of E with negative t. Okay. This is 1 over s plus t. When you have Laplace t cubed, this is 3 factorial. When you have Laplace, say cosine 2t, this will be s squared plus 4. Laplace, let's say sine 3t, say this is 3 s squared plus 1. Okay. Now before we move to the inverse, how to inverse the s into t, okay, back to the t, let me just give you another theorem, okay, for the Laplace, that the Laplace transform is a linear transform. What does that mean is, if we remember, let me write. Okay, maybe take for a while, and if you want to take notes for this, all the 5 different Laplace that we have, I will just focus on this 5 Laplace. If you find another Laplace in your books, I think we just focus on this 5. Okay. And don't forget to work your quiz. Okay, to work your quiz 1. I already give the drive folder, so you could check your drive folder, upload your scan, your scan files, and don't forget to submit your works in the platform. If you have any trouble uh, when you're doing this quiz, just let me know. Please email me. Email me. I already given you all the instructions, I think, in the folder. Also, when you click the link, you will be also given some instructions. Just follow the instructions, and whenever you submit, don't forget to upload your PDF file. Next week, probably we will have our midterm. I will take the hours on, I think, Friday, I think will be better. The topics is from the beginning until the higher order differential equations. Okay. All the topics that we discuss in class. That will be the main topic. And today or tonight I will upload the notes, okay, my notes, and a little bit homework that you can do. Okay, let me give you one theorem, okay, on this Laplace that is essential. So if you consider that you have the Laplace functions that is, let's say, a function of t, and then multiply with a constant alpha plus another constant and another function g. Remember, in integrations, we can split these integrals, right? And then we can factor out alpha and beta. So alpha, beta are constant. So we can set up alpha goes outside, and this will be multiplied with this, and plus another integral. Okay. So whenever this integrals is converged for s is greater than c and a constant, then we can write the Laplace. We have alpha plus beta g. Then we can write this is alpha Laplace of f of t plus beta Laplace of g of t. Or we can simply say alpha becomes fs plus beta becomes g. So we can say that Laplace is a linear transformation.
Professor, what do you
Yes.
mean by linear transformation?
Linear means that we can set up, if we have this constant f beta g, we can separate these integrals, right? So we can do that also in our Laplace. It means that it's linear transformation. It's linear transform. We can linearly transform the Laplace. So when you have Laplace, for example, let me give you an example here. So when you have Laplace, maybe tan e negative 3t, for example, minus 5t plus 8. We can take this each functions with each Laplace. Okay, so we can write this is actually tan Laplace of e negative 3t minus 5 Laplace of t and plus 8 Laplace of 1. This is what I mean by linear. Okay. Linear transform. And then we can set this to be 10 divided by s plus 3 minus 5 uh, s squared, right? Because it's t1, right? So it's just 1 and equal with power of 1 plus 8 divided by s. And you can just, if you want to add all this component, that you can do also, but you can just stop here.
Okay, thank you, Prof.
Yeah.
I got it.
Okay, any questions? No? Will Laplace be in the midterm? No. I think I said before, the midterm will be introductions, the first order, and the higher order. Okay, I think it's too much if I put in the midterm. So Laplace will be, uh, if not, just take one quiz about Laplace, or I will move it to final exam. But I think uh, Laplace will be, I think in the in its own quiz. It has its own quiz. Okay. Okay, let me check. Okay, now I will give you another theorem. So first, linearity. Laplace is linear transformation. The second theorem is about existence and uniqueness. So when Laplace transform exists, that's uh, I think a good questions to analyze um, our understanding in Laplace. Okay, now let me just skip this and make a new page. So when uh, Laplace exists, okay, a function of t, let's say, is we call exponential order as t goes to infinity if the function's absolute value is less equals for some m, a constant m, multiplied with e with power of c t. For some constant, this is for some constant m, right? Or maybe white with green. M and c, the small c, for sufficiently large t. Let's say the t is greater than p naught for some t naught. Well, it basically says that there is a t that greater than the previous one. Okay. The simplest way to check, okay, the simplest way to check is checking the limit. Okay. If limit exists and finite, usually 0, then f of t is exponential order, is of exponential order. So Laplace need to be checked with this limit. Okay. Okay, and then we can say from this exponential order, the existence of Laplace. Let f of t be continuous and also exponential order for certain constant c. Then f capital S, capital F of variable s is Laplace of f of t is defined for all s greater c. Okay, how do we practically see these definitions for the existence? If f of t is exponential order, okay, so let's say f of t is exponential order, then as implications, we are going to see that this function of t will equal or less equal of m is a constant, of e with power of ct for all t positive. For simplicity, let's say that t0 is 0. Okay. Okay, let s greater c. Or in other words, we could say c minus s is less than 0. And then using comparison theorem, using comparison theorem in calculus in the integration part, integration in the integration, we have a comparison theorem, right? The improper integral defining the Laplace will be exist if so we take the m e c t dt, we could take out the m, or let me just combine this st with ct. This will be c minus st dt is equal m, and take the results of the integrations, e c minus st over c minus s, right? Take it from 0 to infinity. And this will be equal, let me write a little bit left here. And this will be equal to m over c minus. Okay, so the Laplace of ft will be exists if this integration exists. Okay, so how this to be exists? Then we need to have the c minus s as 0, and also m a constant. And when we find the integral using the Laplace integral, we see that this is exists, okay, having the m over c minus s. So this theorem is true, okay, so for all s greater than c. Okay, now aside from the existence, we can also analyze the uniqueness. But we need um, to check that the Laplace exists, and then we can check after existence, we can check the uniqueness. Okay, the next part is the uniqueness of Laplace. So let f of t and g of t be continuous and of exponential order. Suppose exists a constant c, okay, or maybe the big C. screen, such that when we Laplace these two, f of t and g of t becomes f, capital F, and capital G for all s greater c, then f of t is equal to g of t for all t positive from 0. So the existence and uniqueness, we can also see if they are piecewise continuous functions, we can also use this theorem of existence and uniqueness. For let me just write notes. For piecewise defined function, the function continuous except at discrete at its discrete set of points. But we still can consider using this existence and uniqueness. So if you have a piecewise, you can also check whether it's with the existence and the uniqueness of the Laplace also. Okay. Okay, for piecewise, because we already define all this existence and uniqueness, if you want to transform the piecewise, for example, evaluate Laplace of function of t for function that is 0 and 2 for 0, 3 and t is with 3. So if we looking at the piecewise and we check 1, 2, 3, 1, 2. Okay. From 0 to 3, it's 0, 0, right? And from t greater equal 3, so we start from here and going to the right. Okay. And this is our piecewise graph, right? Continuous functions graph. So this Laplace is defined by the sum of two integrations. So first, let me write the whole Laplace. Okay. Then we can set up the sum from 0 to 3 of this 0 dt plus 3 infinity of e negative st to dt. The left part will be 0, then we just have the if we integrate this, 2e negative st negative divided by s from 3 to infinity. We can simply call this as 2 because it's actually 0 minus minus, right? So we can have this 2e negative 3s over s, and s should be positive. Okay. The next part is the inverse of Laplace. I will just go some briefly inverse of Laplace. We continue again the inverse part on Monday. Okay. Okay, maybe we can have a feedback later. Okay, maybe around 11:45. 45. Okay, so linearity, existence, and uniqueness. The next section is the inverse of the Laplace. Okay, inverse transform. Okay, if we start with f, capital F, with function of s, we call this with Laplace. Okay, we can see this is what we are doing before, right? Then we can take the function of t as Laplace of the capital F, like that. So we say that the f of t is the inverse Laplace transform. Maybe write with green. Inverse Laplace. Okay. Remember, we have, let's say, if we have 1, we can say that this is Laplace transform or inverse Laplace transform of the 1 over s, right? Or if you have t is the Laplace transform of 1 over s squared. So we could have another table. We could have another table that set up this Laplace and the inverse. Okay. Let me just copy from the last part. Okay. Let me copy the left, just the left, to see the connection. So Laplace transform and Laplace inverse. So Laplace inverse of C over S is become just a C. Laplace inverse of 1 over S minus lambda. Well, in your textbook, I just noticed that usually the bracket using this kind of bracket, but for me that's still okay. As long as you have a Laplace and you have something inside, you get the brackets. This will equal to E with lambda t. And now something different you will notice here that I will just write 1 over S with power of n. This will be t n minus 1 over n minus 1 factorial. This is just to make short because this n factorial divided by s n plus 1 is not common, so we need to just to rewrite the forms, okay? Rewrite the forms and make it just 1 over s with power of n. And the other part we can write, I think easily, we can write from s squared plus beta squared. This will be cosine beta t. Okay. Okay, again, in the inverse Laplace, we also have the linear property, the same with the Laplace transform, because it's just the inverse of Laplace. So we could have the Laplace inverse is also, or maybe is a linear transform. So if you have Laplace transform of alpha f of s plus beta g of s, this will be alpha Laplace transform of f of s plus beta Laplace transform of g of s. Okay, where f and g are the transform of some functions f and g. And alpha and alpha beta are constant. Okay. So why we need to know the inverse of this Laplace? Because to solve differential equations, we can Laplace transform, and then we can invert back, and we can find the solution. Okay? But that will be a later for solving that as well. Okay? Okay, let me just give you a quick example. So if your capital F is 1 over s minus 2, your function of t, we can directly get that this is e, right? Exponent to t. Okay. If you have, what happens if you have 1 over 2s minus 1? So we could force out the structure, and we need to make the structure becomes 1 over s minus lambda, right? So we could factor out 2, so 1 over 2 s minus half. So what we are going to do here is, this is half, and then if we want to write in the Laplace symbol, we can write in the Laplace inverse of the whole thing, the 1 over s minus half. Or we could write half e with power of half t. Okay. This is f of t. You have 2 with over s power 5. Remember that if we have a plus inverse of 1 over s5, this will be equal to t, or maybe just let me just write with n first, n minus 1 and n minus 1 factorial. So what will happen here is the ft, this will be 2 multiplied with Laplace inverse of 1 over s power of 5. So this will be 2 multiplied with t n minus 1, so 5 minus 4, minus 1, so it's 4, divide by 4 factorial. Or we could say that this is t with power of 4 divided by 12. Okay, so we start slowly see the, and makes you familiar first, okay, before we go for the differential equations. Okay. Now if we have 1 over s squared plus 3, what is it? So if we took the Laplace inverse, if we remember what happened with this is, we call the sine beta divided by beta, right? Or 1 over b. Remember that the sine beta should have, let me write here, that the Laplace of sine, we need to have beta over s squared plus beta squared, like that. So we need to multiply with 1 over beta to make it 1, right? Okay. Now the ft will be Laplace transform or inverse 1 over s squared plus 3. That is, the beta is square root of 3, right? 1 over square root of 3 sine square root of 3t. Okay. Let me give you more examples like this to give you more familiarity. If you want to inverse transform or inverse Laplace these equations, if you take slowly and take the linear approach and write one by one to make sure that we understand, this will be 1 over s plus 1 minus 6 Laplace inverse 1 over x squared plus 4, and then plus Laplace inverse 1 over s with power of 4. This is 5, so f of t. 5, this is e minus t, minus, this is 6 over 2, this is sine 2t, plus t cubed divided by 6, right? And minus 1 factorial, 3, 2, it becomes 6, right? So f of t becomes 5. Okay. Okay. What will happen if we need to evaluate the inverse Laplace of negative 2s plus 6 divided by s squared plus 4? What will happen? We can separate this Laplace. So the first one is negative 2s x squared plus 4, and maybe we will write. Let me write slowly. This becomes this, okay, and then we can take the negative 2 outside, and then Laplace inverse of s squared plus 4, and then plus this will be 6 Laplace inverse 1 over x squared plus 4. Okay, now whenever you have x squared plus something in the denominator, we will get cosine or sine, right? The problem is the top one. If you have s in the top, then we will be going to be cosine. If you have a constant like 1, it will be a sine, right? So we will have, I think this is directly cosine 2t, right? So we can just write negative 2 cosine 2t. And this is supposed to be having 2 here for the beta, but it's not, so we need to divide by 2, right? So we have plus 3 sine 2t. Okay? Believe that's not too difficult to see. Now what happens if we have the inverse of s squared plus 6s plus 9 divided this is s minus 1, s minus 2, and s plus 4. Now we are going to take partial fraction. I hope you still remember partial fractions, okay? Partial fraction. So this is actually one way to solve. And I think it's important because we are going to use partial fractions many times. So first, we are doing the partial fractions of this. And I think this is the simplest, I think one of the simplest partial fractions. We just take s minus 1, s minus 2, and s plus 4, right? So take the SAA inside here that we are going to evaluate. So A, s minus 2, s plus 4, plus B, s minus 1, s plus 4, plus C, s minus 1, s minus 2. It needs to be equal to s squared plus 6s plus 9. Okay, let me give you some cool tips for solving these partials. Okay? You see that when s is equal to, this part is 0, right? This part is 0, right? And you can calculate 4 plus 12 plus 9, right? And you can calculate this easily. So b multiply with 6b multiply with 6b equal to 625, right? So b is 25 over x, so over 6. And we can also set s equal 1. Let me write with red color. This one is 0, this one is 0. So we are going to evaluate this. And we are going to have negative 5a equal to 1 plus 6, 7 plus 9 is 16. So a is negative 16 over 5. And same thing, take the s equal negative 4 to make the other one 0. So this is 0, 0, and we are going to have c will be negative 5, negative 6 is 30c, negative 4 is negative 24, plus 16 is 8. So 8, negative 8 plus 9 is 1. So c is 1 over 30. So you will get this all this constant, and you're going to put through all this constant into this each fraction. And I think 1 over s minus 1, you can easily go to the exponent, right? Exponent root. So we will have, finally you will have negative 16 over 5e with power of t plus 25 over 6 e with power of what? 2? 2t plus 1 over 30 e with power of negative 4t. 4t, okay? Okay, I think I will just stop here, okay, and then give you feedback, and we can have some conclusions, and we can continue this Laplace transformations next Monday, okay? Well, before we stop, is there any question? Is there any questions? Okay, so my plan is the midterm will be on Friday, so you'll be having some sort of a few days to prepare, and I will give you homework to prepare you for the midterm. Okay. Okay, the answer for homework 1. Okay, I hope I can prepare for you this weekend for the homework 1. But I think most of you did, I think, very well. Just a few notes that I think I already mentioned. Some sort of integration techniques that you need to remember. Okay. So I think that's the I think calculus problem. The calculus problem. Okay, now we are going to set up the feedbacks. So let me stop this sharing here. And then share screen, the second screen. Okay, I hope you can see my screen. Okay, and I hope the time limit in each question, I hope it's enough. We only have, I think, 2 or 3. One short questions. The other 2 is a little bit calculation, so you need to, I think, prepare some paper and pen and paper. Okay. Or if you want to prepare calculator, also fine. Okay, let me. Okay, I think we can start. Okay, as usual, you have 2 or 3 questions. Prepare your student ID. Okay. I think it's student ID, that's okay. So I can map your score to the system. Okay, we will start. 3, 2, 1. Let's start. Okay, give you some time limit. Okay, don't forget the procedure. Okay, don't forget the procedure. When you have the differential equation, always think from the homogeneous one. Okay, always think from homogeneous one, and then you can make a conclusion for the particular one. Okay. So think the YC first, and then you can decide the YP. This is just to make sure whether it's true or false. No need to calculate the end result. But if you want to check, you can also check. Yeah, it's false because of duplicity. Okay, remember, whenever you have duplications, you need to multiply with x or x squared or x cubed. That depends on the situation. Okay. Okay, good. Okay, second one. 3, 2, 1, start. Okay, I hope 2 minutes enough. Remember to need to use the auxiliary equation, making the differential equations into polynomials or quadratic formula, right? And then find the roots. And depends on the roots, you can make some conclusions, whether it's distinct roots, it's equal roots, or maybe having a complex, conjugate complex. You can open your notes how to write this structure. Okay, if you have those roots, okay. Maybe it has the exponent, or maybe it has the sine or cosine, right? Well, if you see from the options, it has sine and cosine, so probably this is going to be conjugate complex, right? Conjugate complex. So for conjugate complex, you need to define it's always the structure, always alpha plus beta I. I is the imaginary number. And you need to define whether there's alpha and how much is it, how much is beta. And of course, we have initial value 0 and 2. Okay. 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 Okay, one more question. This is a little bit long, so I hope you can solve it. Okay. Okay, 6 minutes to solve. 6 minutes to solve. I hope the time is okay. I push you through some short time here to let you familiarize with the differential equations problem. Okay, good. There are some students got correct answer, right? Okay, really good, really good. But still, the winner is yeah, yeah. Okay, still okay. Okay. I think that's it for today. And please write your student ID and give me your feedback if you have any. Maybe if you want to have like more practice for the preparations for the midterm, I can prepare, and I will plan. I'm planning to give you a homework for the higher order to help you prepare your midterm. And don't forget to work your quiz. Okay, don't forget to work your quiz. Okay, at least tomorrow you should try. Okay, or maybe Sunday morning also. Okay, and please make sure you work by yourself. Okay? I didn't say that you can have a group discussion, but it's better to work individually to check whether you understand or not. Okay. Yeah, the homework is actually for practice. Okay, for practice. Usually, I'm not really checking one by one. Whatever your submissions for homework, but I would check for some notes that maybe generally if you can do it, I think that's still okay. But if you mostly you still confused on some problem, that I need to make sure that you can do it on the midterm. Okay. Okay. If there is no questions, then uh, I will stop this sharing and see you next Monday. Okay. See you next Monday. So okay, I will stop the recording.